Hello everyone, welcome back to my study. Today we are discussing question number 8 of problem 20.8. That is, we are evaluating integrals using residue theorem. Before going to the video solution, please do subscribe my channel and watch the video. You can also check my channel for more solutions of chapter 20 and you can see my playlist of chapter 20, solutions of chapter 20 here. There are more videos of solutions of chapter 20. Please do like my video if it is helpful to you. So first question, integral of z dz divided by z minus 1 into z minus 2 all square. The region is given by mod z minus 2 equal to 1 by 2. That means the circle with the center 2 and the radius 1 by 2. Question is given by z dz divided by z minus 1 into z minus 2 all square. And the region is center 2 with the radius 1 by 2. That is the circle with the center 2 and 2.5, also 1.5. Singularity z is equal to 1 and 2. So, z is equal to 1 is not inside the circle. Z is equal to 1 is outside the circle. So, z is equal to 2 is inside the circle. So, this is our singularity. So, by residue theorem, this integral z dz divided by z minus 1 into z minus 2 whole square is equal to 2 pi I into sum of residues inside the region. Here residue at z equal to 2 f of z. Z equal to 2 is z equal to 2 is pole of order 2. Pole of order 2. So residue at a pole of order 2 is 2 pi I limit z tends to 2 d by dz of z minus 2 whole square into f over z. That means 2 pi I into limit z tends to 2 d by dz of z minus 2 whole square into f over z. That means z by z minus 1. So differentiating this function and putting limit z tends to 2. Differentiating this function, this means z minus 1 minus z divided by z minus 1 whole square. That means denominator z minus 1 into derivative of numerator is 1 minus numerator into derivative of denominator is 1 and denominator whole square. That is 2 pi I. Substituting the limit z equal to 2, we get minus 1 divided by 1 square. 2 minus 1, 1 square. That is minus 2 pi I is the answer. So next question. Question number 2. Integral of z square plus 3z square plus 2 divided by z minus 1 into z square plus 9 dz with the mode z minus 2 equal to 2. Over the circle, mode z minus 2 equal to 2. This is circle with the center 2 and the radius 2. So, circle with the center 2 and the radius 2. That means 1, 0 are there. So, 3, 4. And z equal to 1. Z square plus 9 is 0 when z is equal to plus or minus 3i. These are singularities. Now, check whether it is inside the circle or not. Clearly z equal to 1 is inside the circle and z is equal to plus or minus 3i. This is I, 2i, 3i, also minus I, minus 2i, minus 3i. If you want to check if it is inside, put z is equal to 3i here, 3i minus 2. Modulus of 3i minus 2 is square root of 3i square. 3i square is minus 9 plus square root of minus 2 square. That is, square of minus 2. That means 4. This is root minus 5. That is root 5i, and which is greater than 2. That means 3i also minus 3i outside the circle. So this is outside the circle. Z is equal to 1 is inside the circle. So by residue theorem, we get integral over C 3z square plus 2 divided by z minus 1 into z square plus 9 dz equal to 2 pi I into sum of residues inside the sum of residue at the singularities inside the circle. Z equal to 1 is the only singularity inside the circle. So residue at Z equal to 1 f of Z. Also Z equal to 1 is a single pole. So residue at a single pole is limit Z tends to 1 Z minus 1 into f of Z. That means this is equal to 2 pi I limit is Z tends to 1 Z minus 1 into f of Z is 3z square plus 2 divided by z square plus 9. 2 pi I into 3 plus 2. Putting z equal to 1, 3 plus 2 is 5 divided by 9 plus 1 is 10. So 2, 5, 10 cancel. Answer is pi I. Third question. Integral over C dz divided by z square plus 4 whole square with the mod z minus I equal to 2. That means center I and radius 2. Let's see the solution. The region given by I-centered circle with the radius 2. That means 0 is there, also minus I is there, also 2i and 3i also there. That means radius 2. 2 is our radius. I is the center of the circle. Yet singularities at z square plus 4 equal to 0 when z is equal to plus or minus 2i. So plus or minus 2i are our singularities. You can see minus 2i is not inside the circle. Z is equal to 2i is inside the circle. So our singularity inside the circle is Z is equal to 2i. Now by residue theorem, integral over C dz divided by z square plus 4 whole square is equal to 2 pi I into residue inside is Z is equal to 2i. Residue at a singularity inside the circle. Residue at Z equal to 2i f of Z. Now this is integral over C dz divided by z square plus 4 whole square. That means we can write it as z plus 2i into z minus 2i whole square. That is z plus 2i whole square into z minus 2i whole square. So both are pole of order 2. So our singularity Z is equal to 2i is of pole of order 2. So the residue at pole of order 2 is limit Z tends to 2i d by dz of Z minus 2i into all square into f of Z, which is equal to 2 pi I limit Z tends to 2i derivative of Z minus 2i whole square into f of Z. That means dz divided by 1 by f of Z is 1 by Z plus 2i whole square. So the derivative is 2 pi I limit Z tends to 2i. Derivative is minus 2 divided by Z plus 2i whole cube. This is 1 by z square, this derivative, this z plus 2y all raised to minus 2. So derivative is minus 2 z plus 2y all raised to minus 2 minus 1. That is minus 2 z plus 2y all raised to minus 2 into z plus 2y all raised to minus 3 is the derivative. Now that is minus 2 divided by z plus 2y all cube. Now putting the limit z equal to 2i, we get minus 2 divided by 2i plus 2i, 4i all cube. That is minus 4 pi I divided by 4 cube into I cube is minus I. Now I minus minus cancel, and also 1 4 cancel from numerator and denominator. We get pi divided by 4 square. That means pi by 16 is the answer. If this solution helpful to you, please like the video. And those who are watching my video without subscribing my channel, please do subscribe my channel. Also, you can check my channel for more video solutions. Thank you for watching.